From last time, we defined this notion of sigma algebra. The idea behind the sigma algebra is that the sigma algebra is where we're going to define the measure of the set. It's kind of defining how large the set is. So now let's start to move into the definition of measures. All right, so let B be a sigma algebra on some set X. We say a measure. What do I mean by that is a map that assigns a value. Let's assign a real value. So here's from B to R. So it assigns a value to every subset that's contained in your sigma algebra that satisfy the following. So first of all, it has to map the empty set to 0. The empty set always have measure 0. There's no problem with that. Second, it has to be positive. So here, what I mean by positive is that the mu, when you want to assign a value for each subset, you assign a value between 0 to positive infinity. Notice here I used a close bracket. So there can be some element in B that has measure positive infinity. If you think about the real line, you do the usual Lebesgue measure, and the mu of this entire real line will be infinite. So you can allow it to take the positive infinity as your measure. So later on in this course, we're going to relax this positivity assumption. We'll study the sign measure when you allow the mu to take negative values, and eventually we'll allow mu even take complex value. And later on, if you continue studying, you may see there are examples where mu is allowed to take operator value like matrix. Anyways, that's beyond this course. Let's continue. The third property I need this measure mu to satisfy is this property that we call the sigma additivity. So what do I mean by sigma additivity is that if I have a sequence of disjoint sets in the sigma algebra, let's call it AN, then the measure of their union, so this is their union, is going to be equal to the summation of their measures. So this is the infinite sum. So here sigma again is really about countable union. So we're saying the measure of a countable union of disjoint set is the sum of their measures. All right, so just clarify a bunch of notation. So if I just give you a set X and a sigma algebra, so this is sometimes called a measurable space. So here the measurable really means we can assign some measure. We know what kind of set we can assign measure. That's the sigma algebra. And if I give you a measure on that, so this triple X, B, and mu, we'll call it a measure space. So here, when I talk about a measure space, there has to be a measure on it. All right, so before we move into their properties, let's start with some notion, some examples first. Let's do some examples. All right, so the first two examples, again, let's do some quite trivial ones. So if I just let mu of any set to be equal to 0 for all B in the sigma algebra, then you can check that this mu satisfies all the conditions. For example, it maps the empty set to 0. Well, it maps everything to 0. It satisfies the positivity. Well, it maps everything to 0, which is non-negative. And the sigma additivity, well, everything is 0, so there's no doubt it satisfies the sigma additivity. So this is a measure. Even though this is not a very interesting one, it just kills off everything, like it measures everything to 0, but it's a measure. Second, well, if I just let mu to be the following, so if I do the other extreme, I want to say, well, B is going to be positive infinity. Well, for all B in B, well, first of all, I cannot do that. It's not going to give you a measure because if B is the empty set, it has to assign the value 0. So let's just assign B a infinite value when B is non-empty. And when B is the empty set, well, we have no other choice but to assign it measure 0. So this is also a measure. You can verify all the conditions. It maps the empty set to 0. Everything else is infinity, so it satisfies all the other conditions you like. Again, this is not a very interesting one because, well, most of them are infinite. So it's basically saying every set is huge except the empty set, which has measure 0. So again, not so interesting. All right, so let's do some a little bit more interesting ones. All right, let's do the third one. Third one, this is called a Dirac's measure. So I'll use the notation. So here's the notation. So here, if I take some point x inside the space x, the Dirac measure delta of x is defined by the following. So it takes a set, say B, from your sigma algebra, and it returns one of the two values. So it will return a value 1 if x is inside this B, and it will return a value 0 if otherwise, if x is not inside B. All right. So basically, this Dirac measure will always give you a value of 0 or 1. All right, so we're going to show that this is in fact a measure. All right. So let's claim it's a measure. So here's the proof. Delta x is indeed a measure. Well, what do I need to show? Well, to show it's a measure, I need to prove it satisfies all the conditions. So first of all, delta of x evaluate on an empty set. Well, empty set contains nothing, so x is certainly not inside the empty set. So by definition, it assigns the empty set a measure of 0. The second, delta of x certainly maps the B into, well, either 0 or 1. So it's certainly a positive measure. So this satisfies the positivity condition. And let's show the sigma additivity. All right, so let's let An be a sequence of measurable sets, and they're disjoint. So n going from 1 to infinity, containing B, and let's say they're disjoint. All right, so let's consider the following. So to show the sigma additivity, I need to evaluate the measure of the union of the set. Okay, so let's consider the set or the measure of this set. Well, there are two cases depending on whether this union contains the point x or not. This measure has two cases. So case 1, suppose that x is contained in this union of An, so in which case the mu of, sorry, I shouldn't say mu, I already gave it a name. Let's use the Dirac measure delta of x. So here is the delta of x. So the measure I assign to this infinite union, if x is an element in there, well, by definition, this is equal to 1. And in this case, well, I need to show that it's equals to, so the goal is to show that this is equal to the summation of delta of x of An. So that's our goal. All right, so let's consider what is delta x of An. Well, when x is in the union, so because x is in the union of these An, so x has to be in one of them. So there exists a case such that x is inside, say, AK. All right. So for that k, we know delta x of this particular AK will be equal to 1 because x is inside AK. Well, how about the others? Now, for every n not equals to k, well, our assumption is that these set An are disjoint. So by An disjoint, We know that AN and AK has to be disjoint, so AN intersect AK is going to be empty. Now X is an element inside AK. So in other words, X cannot be inside AN. All right, so the conclusion is X is not in AN. And because of that, the delta of X assign this AN a measure of 0 because it doesn't contain the point X. So in other words, in this case, all the delta of X of AN is equal to 0 except there's one of them, AK, where you assign to be 1. So in this case, this summation, n going from 1 to infinity of delta of X of AN, well, it's just going to be adding a bunch of 0, except there's only one non-zero term, which is delta of AK, which is equal to 1. And in this case, it's equals to the union, well, the delta X of the union of this AN. All right. Well, the second case is quite similar. It's actually slightly easier. Suppose X is not inside this union, n going from 1 to infinity of AN. Then we know the delta of X of this union because X is not in there. We assign a value of 0. Now, when X is not contained in the union, it means it's not contained in any one of them. So this implies X is not in AN for all n. All right. And by definition, when X is not in AN, the measure of this AN will be equal to 0. Well, also in this case, the summation of n going from 1 to infinity of these delta of X of AN, well, because each one of them is going to be 0, that's equal to 0. So that shows that the union measure is equals to the summation of all the measure. Anyways, we just show that these delta X satisfy this sigma additivity. So we have that delta X is indeed a measure. And now let's do a fourth example. It's more about how can we construct a new measure from some known ones. So let's assume that we have some measure, say mu of X, and then another one, let's just say mu1 and mu2 are measures on some X and B. All right. So let's just, for convenience, let's assume that they're finite. So mu1 and mu2 are finite. So in other words, the mu I of any set is not equals to infinity. Let's make this assumption. Then I can construct a new measure by doing the following. So let's pick some scalar, let's say t1 and t2 greater than or equal to 0. Then let's let mu to be t1 mu1 plus t2 mu2. So in other words, if you want to evaluate the measure of a B, well, what you can do is you measure it under mu1 and measure it under mu2, and then you multiply by t1 and multiply by t2, you add them up. All right. So you can verify that this mu is a measure. Okay, I'm not going to do the proof. I'll leave this as an exercise. It's a quite easy one. You just use mu1, mu2 are measures, and you can show this mu is also a measure. That's fairly simple. Anyways, so what's this property? What this example is telling us is the following. Well, this procedure is really doing what they call linear combination. So we're really showing that the set of all measures satisfies some linear condition or forms a linear space. Okay, so we'll look at this measure space, like all the measures on these X and B eventually later on in this course, it will have some nice properties. But let's keep in mind, we have a linear structure on the set of all measures. All right, so before we go into the properties of measures, let's just give some definition. There are a lot of different notions of measures. So let's give a few that are quite useful for now, all right? So let's let mu be a measure. Then let's give the following notation. So we say mu is finite if that mu of b is not equal to infinity for all b. So mu of b is less than infinity for all b in B. Well, we will eventually see, well, because the measure is monotone, we'll show that when we talk about the properties, this is actually equivalent of saying the mu of the entire space is finite. Okay, when mu of x is finite, we have mu of any b will be finite. We'll show that eventually, but here's the definition of finite measure. And second, we say that is sigma finite if that this x itself may not be finite measure, or mu of x may not be finite, but we can find some larger and larger space with finite measure. So if we can write x as a union of n going from 1 to infinity of some en. So these en's are going to be inside the sigma algebra. And we have that the mu of each of these en is finite. So x, even though x itself may not have finite measure, is equals to a union of a bunch of finite measurable sets. So one example of a sigma finite measure is the Lebesgue measure. So if you think about the real line, the measure of the real line is infinite, but you can write the real line as the infinite union of these negative n to n, where each of these negative n to n has finite measure of 2n. All right, so this is called sigma finite. It's going to be quite useful eventually. And let's give some other notation. So let's call it a semi-finite. So mu is semi-finite. If the following happens, well, if that for every set, let's say E, or let's use F, goes the same one as the course note. So suppose I have an F inside B, even though this F may not be finite, I will say, well, let's say mu of F is also non-zero. Well, I want to say that if F is infinite, then I can find some finite measure inside this F. So then there exists an E contained in F such that mu of E is going to be less than infinity, well, and positive, all right? So here I need it to be strictly positive, but less than infinity. So if for every non-measured zero set F, I can find a subset that has a finite non-zero measure, well, then I call this measure semi-finite. So here I really need this mu of E to be strictly positive, because otherwise you just take E to be the empty set. All right, so lastly, let's call mu is a probability measure. Probability measure. Well, if the following happens, if mu of the entire set is equal to 1, all right? So this is going to be a special kind of measure that you'll be really interested if you coming from a probability background, or if you're in the math finance program, you'll see a lot of probability measure eventually.